They called it the television of the 1800s, a machine that could transmit moving images across vast distances without wires. No electricity required, no broadcasting stations, just pure mechanical genius decades before anyone dreamed of screens in their living rooms. This wasn't science fiction. This was real, built by a forgotten inventor who saw the future before the world was ready for it. His name has been erased from history, but his machine changed everything. And today, we're bringing it back to life. The year was 1884. Thomas Edison was still perfecting the light bulb. The telephone was barely a decade old. Yet in a cramped workshop in Manchester, England, a clockmaker named Samuel Hartwell was building something that defied every law of what was possible. He called it the mechanical vision transmitter. What it did was impossible. What it promised was revolutionary. What happened to it was tragic. Samuel Hartwell wasn't supposed to be an inventor. He was a simple clockmaker fixing pocket watches and grandfather clocks for the working class of industrial Manchester. But Hartwell had a problem. He was going blind. Slowly, inevitably, the fine details of his craft were slipping away. Instead of accepting defeat, he became obsessed with a single question. If he couldn't see the intricate gears and springs up close, could he somehow make them appear larger, clearer, transmitted to where he could see them? That obsession led him down a path no one had walked before. Hartwell began experimenting with rotating discs, each one perforated with precisely cut holes. He discovered that when light passed through these spinning discs at exactly the right speed, it could break down an image into individual points of light and shadow. More importantly, those points could be reassembled somewhere else. The principle was brilliant in its simplicity. Take any image, break it into tiny fragments, send those fragments through a mechanical system, and reconstruct them at the destination. But Hartwell went further. He didn't just want to transmit still images. He wanted motion. He wanted life itself to travel through his machine. Working 18 hours a day in his workshop, he built a system of synchronized rotating discs connected by an intricate network of cables and pulleys. The transmitting disc would scan an image line by line, converting light and shadow into mechanical motion. That motion would travel through the cable system to the receiving disc, which would reconstruct the image in perfect synchronization. The first test was a candle flame. Hartwell placed it in front of his transmitting disc, cranked the handle, and watched as the flame appeared, flickering and alive on the receiving end 20 feet away. Then he tried a pocket watch, its hands moving in real time on both sides of the room. Finally, he pointed the machine at his own face and saw himself transmitted mechanically, watching back. Word spread through Manchester's scientific community like wildfire. Here was a machine that could do what no one thought possible: send moving images across distance using nothing but mechanical precision. The Royal Society took notice. Investors began circling. Hartwell's workshop became a pilgrimage site for engineers and scientists from across Europe. But 1884 was not ready for television. The infrastructure didn't exist. There were no power grids to rely on, no mass production capabilities, no understanding of how such a device could be commercialized. More critically, there was no content to transmit. No studios, no cameras, no programming. Hartwell had built the perfect solution to a problem the world didn't know it had. The machine itself was a marvel of engineering that wouldn't be matched for decades. Each disc was hand-machined to tolerances that modern manufacturers would respect. The hole patterns were calculated using mathematical principles that wouldn't be formally described until the 1920s. The synchronization system was so precise that it could maintain perfect timing across distances of up to half a mile. Hartwell's breakthrough was understanding that images could be serialized. Every picture, no matter how complex, could be broken down into a sequence of light and dark points. Transmit those points in the right order at the right speed, and you could reconstruct the original image anywhere you wanted. It was the same principle that would later power electronic television, but Hartwell did it with gears, springs, and mechanical precision. The transmitting station looked like a massive clockwork mechanism. A hand crank provided the power, turning a series of gears that drove the main scanning disc. This disc, nearly 3 feet in diameter, was perforated with 240 holes arranged in a precise spiral pattern. Behind the disc, a powerful oil lamp provided illumination. The subject to be transmitted stood in front of the disc, lit by the lamp passing through the spinning holes. As the disc rotated, each hole would scan across one horizontal line of the image. The light passing through would vary in intensity depending on whether it hit a bright or dark part of the subject. This varying light was captured by a selenium cell, one of the few electronic components in the entire system. The selenium cell would convert the light variations into electrical resistance changes, which drove a mechanical relay system. Here's where Hartwell's genius truly showed. Instead of trying to send electrical signals across long distances, which was unreliable with 1880s technology, he converted the electrical variations back into mechanical motion. A series of electromagnets would pull and release a mechanical linkage system, creating physical motion that perfectly matched the light variations at the transmitting end. This mechanical motion traveled through a cable system to the receiving station. The cables weren't just wires, they were precision-engineered mechanical linkages, more like the control cables in a ship or aircraft. At the receiving end, the mechanical motion drove another set of electromagnets, which controlled the brightness of a gas flame positioned behind an identical scanning disc. The receiving disc was synchronized with the transmitting disc through a mechanical governor system. Both discs had to rotate at exactly the same speed, scanning their respective images line by line in perfect unison. When everything was aligned, the varying gas flame would recreate the original light pattern, and the image would appear on a ground glass screen behind the receiving disc. The resolution was remarkable for its time. With 240 lines per image and 16 images per second, Hartwell's system could transmit moving pictures with enough detail to recognize faces, read large text, and follow simple actions. The images were black and white, but they were sharp, stable, and utterly impossible by the standards of 1884. Demonstrations drew crowds of hundreds. Hartwell would transmit live images from one end of Manchester to the other, showing street scenes, people walking, horses pulling carriages. The images would appear on the receiving screen in real time, a ghostly mechanical window into a distant location. Newspapers called it witchcraft. Scientists called it revolutionary. Investors called it profitable. But the world wasn't ready. The infrastructure to support mechanical television simply didn't exist. Installing Hartwell's system required teams of skilled mechanics, precision machined components, and maintenance that few people could provide. The machines were expensive to build and even more expensive to operate. Each installation was essentially a custom engineering project. More fundamentally, there was nothing to watch. Hartwell had solved the technical problem of transmitting images, but he hadn't solved the content problem. There were no programs, no entertainment, no news broadcasts. The machine could show you what was happening somewhere else, but unless something interesting was happening, why would you watch? The economic model was impossible. Unlike later electronic television, which could broadcast to unlimited receivers, Hartwell's system was point-to-point. Each connection required its own mechanical linkage, its own synchronized disks, its own dedicated operators. Scaling to serve even a small city would have required thousands of operators and millions of feet of precision cable. Then came the disaster. In 1887, a fire swept through Hartwell's workshop. The cause was never determined, but the timing was suspicious. Hartwell had been negotiating with several investors, some of whom had competing interests in telegraph and telephone systems. The fire destroyed not just his machines, but his detailed plans, his mathematical calculations, and his prototypes. Hartwell himself was ruined. He'd spent his life savings developing the system, and the fire left him with nothing. He tried to reconstruct his work from memory, but the precision required was beyond what he could achieve without proper tools and funding. He died in 1892, forgotten and impoverished, his revolutionary invention dismissed as an interesting curiosity. The world moved on. Electronic television wouldn't arrive for another 40 years, and even then, it would take decades to reach the level of sophistication that Hartwell had achieved mechanically in 1884. His core insights about image serialization, scanning, and synchronization would be rediscovered independently by multiple inventors, each one unaware of the Manchester clockmaker who had solved the same problems decades earlier. What makes Hartwell's story so compelling isn't just the technical achievement, it's the tragedy of timing. He had built a machine that could do what no one thought possible, but he'd built it in a world that couldn't use it. The infrastructure, the economics, the cultural understanding of what television could be, none of it existed. He was a man with a solution to a problem that wouldn't be recognized for another generation. But here's what's truly remarkable about Hartwell's system. It wasn't just ahead of its time technically, it was ahead of its time conceptually. Hartwell understood that images were information, that information could be transmitted, and that transmission could happen in real time. He grasped the fundamental principle that would later drive not just television, but digital communication, computer graphics, and the internet itself. His mechanical approach was actually superior to early electronic television in several ways. The images were more stable, the synchronization was more reliable, and the system was completely immune to electrical interference. While early electronic television struggled with ghosting, static, and synchronization problems, Hartwell's mechanical system produced clean, steady images that would have been the envy of broadcasters well into the 1930s. The precision of his engineering was extraordinary. Each component was hand-machined to tolerances that modern manufacturers would achieve with computer-controlled equipment. The hole patterns in his scanning disks were calculated using mathematical principles that wouldn't be formally described for decades. The synchronization system maintained perfect timing across distances that would challenge modern mechanical systems. Most importantly, Hartwell proved that the barriers to revolutionary technology aren't always technical. Sometimes the biggest obstacle is simply being too early. The world needs to be ready for an invention not just technically, but economically, culturally, and infrastructurally. Hartwell had solved the hard problem of transmitting moving images, but he couldn't solve the harder problem of creating a world that needed moving images transmitted. Today we take instant visual communication for granted. We video chat across continents, stream movies to our phones, and share live images with millions of people simultaneously. But in 1884, the very concept of seeing distant events as they happened was so foreign that most people couldn't even imagine why they'd want to. Hartwell's story is a reminder that innovation isn't just about solving technical problems. It's about understanding when the world is ready for your solution. He built the future, but he built it in the past. But here's what makes Hartwell's story even more extraordinary. His invention wasn't just mechanically impressive, it was conceptually revolutionary. The principles he embedded in his mechanical vision transmitter were the same ones that would eventually power our modern digital age. Image serialization, pixel-by-pixel scanning, synchronized transmission, real-time processing. These weren't just clever mechanical tricks. They were fundamental insights into how visual information could be broken down, transmitted, and reconstructed. What Hartwell had discovered was that any image, no matter how complex, could be reduced to individual points of light and darkness. His rotating discs didn't just spin, they sampled. Each perforation captured a single pixel of information as light passed through it. That light was then converted into mechanical motion through his intricate linkage system, transmitted across distances and reconstructed on the receiving end. It was analog computing before anyone knew what computing was. The genius wasn't in the gears or the mirrors or even the precision engineering. The genius was in understanding that vision itself could be deconstructed and rebuilt. That moving pictures weren't magical, they were mathematical. Every face he captured, every street scene he transmitted was proof that reality could be digitized, serialized, and shared. Think about that for a moment. In 1884, while the world was still figuring out how to string electric lights between buildings, Hartwell was already thinking in terms of data streams and information networks. His mechanical television was really the first digital communication system, just built with brass and steel instead of silicon and code. But brilliance alone doesn't change the world. It needs context, infrastructure, and timing. And on all three counts, Hartwell was catastrophically ahead of his time. The world wasn't ready for his vision because the world couldn't support it. Consider the economic reality of Victorian England. Most people were still living without electricity in their homes. The telephone was barely a decade old and remained a luxury for the wealthy. The idea of transmitting moving pictures for entertainment seemed not just expensive but pointless. What would people watch? Who would create content? How would anyone make money from it? Hartwell's demonstrations drew crowds, but crowds don't build industries. The technology required skilled operators, precise maintenance, and expensive materials. His synchronization system needed both ends of the transmission to be perfectly calibrated. One slight misalignment and the entire image would dissolve into chaos. It was impressive in a controlled environment, but impossible to scale. The content problem was even more fundamental. Television works because there's something worth watching. In the 1880s, there was no film industry, no broadcast studios, no understanding of visual storytelling. Hartwell could transmit images, but he couldn't create a reason for people to want to receive them. His device was a solution looking for a problem that wouldn't exist for another generation. Even the basic infrastructure was missing. His system required dedicated transmission lines, specialized equipment at both ends, and operators who understood the complex mechanical adjustments needed to maintain image quality. Compare that to the telephone, which needed only copper wire and a simple speaking device. Hartwell's invention was elegant, but it was also impossibly complex for mass adoption. The fire that destroyed his workshop in 1887 wasn't just a tragic accident. It was the inevitable end of a project that had nowhere to go. Hartwell had spent 3 years perfecting his system, demonstrating it to increasingly smaller audiences, and watching his funding disappear. The mechanical television that had once seemed like the future began to feel like an expensive curiosity. What happened next reveals the cruel mathematics of innovation. While Hartwell's invention died in obscurity, the principles he discovered lived on. Decades later, when electronic television finally emerged, it followed the exact same conceptual framework. Paul Nipkow's scanning disc, John Logie Baird's early television experiments, even the electronic system that eventually replaced them all relied on the same fundamental insight that Hartwell had encoded in brass and steel. The scanning principle, the pixel-by-pixel reconstruction, the synchronized transmission, they were all there in his workshop waiting for the world to catch up. But by then Samuel Hartwell was long dead, his name forgotten, his contribution erased from history. This is the paradox of revolutionary invention. The ideas that seem most impossible in their time often become inevitable in hindsight. Hartwell's mechanical television wasn't just ahead of its time, it was trapped in the wrong century. His engineering was Victorian, but his vision was digital. He thought in terms of networks and data streams decades before those concepts had names. Today, we live in the world Hartwell imagined. Moving images transmitted instantly across vast distances. Visual communication that connects people separated by continents. Information networks that carry not just pictures but entire virtual worlds. The mechanical television he built in his Manchester workshop was really the first prototype of the internet. But here's the deeper lesson. Innovation isn't just about having the right idea. It's about having the right idea at the right time in the right context. Hartwell's mechanical television failed not because it was wrong, but because it was too right, too early. The world needed 4 more decades of technological and cultural development before it could support his vision. His story reminds us that the future isn't built by the people who see it first. It's built by the people who see it at the right moment, when society is ready to embrace it. Samuel Hartwell saw the future of communication in 1884, but he was born into a world that wouldn't exist until 1920. The mechanical television that could have changed everything instead became a footnote, a curiosity, a reminder that sometimes the most profound innovations are the ones that arrive too early to matter. In the end, Hartwell's greatest invention wasn't his machine, it was his vision of what the world could become. And that vision, finally, has become our reality.